For today's day in review, we're going to quickly go over the characteristics of acids and bases. If you were absent, here's your daily learning objectives. You were to list 3 properties of acids, list 3 properties of bases, and talk about what does pH measure and what values of pH do acids have and bases have. So we're going to look at 2 schools of thoughts when it comes to characteristics of acids and bases. And this little animation here shows water acting as both. We'll see that acids typically will release hydrogen ions in solution. Bases is something that can accept a hydrogen ion. Bases also are defined as releasing hydroxide ions in solution. The word acid comes from the Latin word acidus, which means sour, and that's one of the properties that acids have is their sour taste. The Arrhenius Model of acids and bases comes from Svante Arrhenius, who's a Swedish chemist. He says that an acid is a substance that dissociates. So remember we talked about dissociation, and this word means that the solute comes apart into ions in the solvent. So salt dissolves in water, and it also dissociates into ions. So Svante Arrhenius says that acid will be something that does dissociate. So if we look at hydrochloric acid, we'd expect to see it dissociate into hydrogen ions and to chloride ions. So in terms of how acids behave, when you put an acid into water, Arrhenius says that you're going to see these hydrogen ions released in solution. And this is the ionization of an acid is what enables acid to be able to conduct. As a pure acid, it will not conduct. As pure water will not conduct, but an acid in water is conductive. So remember we talked about conductivity. In order for something to conduct, you have to have 2 things in place. One of those things is you must have charged particles, and the other thing is those particles have to be able to move. So an acid, as in its pure state, is neutral. The hydrogen and the chlorine here balance one another out, and so the sum of the oxidation numbers is 0. Water is neutral. Again, hydrogen, the oxidation numbers of the hydrogen balance the oxidation number of the oxygen, so that's neutral also. But when you put them in together, it's that dissociation. Water will dissociate the hydrogen and chlorine into their separate ions. Remember that process is called solvation. A base is a substance that releases hydroxide ions in solution. So we're going to see the same thing with the base, that as a single pure sample, bases will not conduct. Water does not conduct. But when you put the base in water, now we get conductivity because, again, we've had that dissociation. So example of sodium hydroxide is a balanced a molecule here, our formula unit. It will not conduct electricity as a pure sample, but if you put it into water and it dissociates into sodium ions and hydroxide ions, then it will be able to conduct. We'll skip that video. Skip that. Now the Brønsted-Lowry model. Brønsted-Lowry pays attention to the hydrogen ion exclusively and wants to follow what happens to that ion or to that proton. Brønsted and Lowry, these were 2 chemists that were working independently of each other but came to the same conclusion. So they're both given credit for this model. They say that an acid is a hydrogen ion donor, which means that if you have a compound that's releasing a hydrogen ion or that proton, it's going to be an acid. So in this example here where we have HCl and water, we can see by looking at the other side of the equation that the chlorine has lost its hydrogen. So we're going to say that the HCl, since the proton is missing, must be the acid because it let go of it. Base is the thing that's going to accept the hydrogen ion. So acids, it's kind of like, playing ball. The acid's going to throw the proton. Whoever catches it is going to be characterized as the base. So in the same example here, if we look at where did this proton go, we'll see it went to the water, because we see it on this side here as H3O. So this case, HCl is acting as the acid, and water here is acting as the base. So one thing that's not shown in this reaction is that oftentimes reactions don't always go to completion, and we'll see that the reverse reaction can also be taking place. So with the Brønsted-Lowry model, not only do we have to figure out which one's the acid and which one's the base, but we're going to also look at something called a conjugate acid and a conjugate base. So look at that same reaction in reverse, the same one that we saw in the previous slide. And a conjugate acid is formed when a base accepts a proton from it says and acid, it should be an acid, accepts a proton from an acid. Let's get rid of this. There we go. Now, if we look at this in reverse here, we see that now the chloride ion on the other side is going to be the one that's accepting the proton. So in this case, the chloride ion is going to act as a base, and the hydronium ion is the one that is getting rid of the proton. So in this case, the water then is acting as an acid. So the conjugate acid is formed when the base accepts the proton, and the conjugate base is formed when the acid donates the proton. So let's look at this example and identify the conjugate acid and base pairs. So looking at ammonium reacting with hydroxide, look on the other side and see who lost a proton. So we see here that ammonium was H4 on the left, H3 on the right. So this is going to be our acid because the proton is missing from there. And water accepted it, so in this case water's the base. Now, if the reverse were true, we're going to find out that water is actually going to be losing the proton to the ammonia if we reverse the reaction. So that means that it's acting as the conjugate acid. And ammonia will turn into the ammonium ion, so that's going to be your conjugate base. Properties of acids, really quickly, they taste sour. They release hydrogen ions in water. pH values, and we'll look at pH next week. Their values are less than 7. They can conduct electricity, remember, only when they're dissolved in water. When they're pure, they will not. And they react with metals. Common acids, sulfuric, that's the #1 acid that's produced in the United States because it's a good intermediate. All the other acids are formed from reacting some sort of salt with sulfuric acid to get those other acids. Phosphoric's used in detergent, nitric in fertilizer, and in your tummy you've got hydrochloric. Properties of bases, remember they taste bitter. They feel slippery. They release hydroxide ions in solution, and they have pH values that are greater than 7. And again, we'll see what that means next week. They also can conduct electricity, but they do not react with metals. And you saw that in that little video that I assigned yesterday. We'll skip over that video. So how do we measure the strengths of acids and bases? Remember, we said acids and bases and salts collectively are known as electrolytes. And that acids and bases are able to conduct electricity. And I said 2 things have to be in place for you to be able to conduct electricity. One is you've got to have those charged particles, and you'll only get charged particles as an acid or a base if you're dissolved in water, so you're dissociated. And 2, those charged particles have to be able to move. So the greater the number of charged particles, the better you're going to be able to conduct. So the more charged particles are present, stronger the electrical current. And a strong acid is going to be one that completely ionizes in solution. So if we look at something like HCl, And if it's strong, that means once we put it into water, all we're going to have is hydrogen ions and chloride ions. You're not going to have any of the hydrochloric acid molecule left. Completely going to ionize. We can check for complete ionization by checking for the conductivity as well. So here's an example of strong acids. Strong base does the same thing. A little rule of thumb with a strong base is if it contains a group 1 or 2 metal and a hydroxide, it's going to be strong because it will completely ionize. We'll skip that video. And don't confuse strength with concentration. Strong acid can be very dilute. You can have a drop of hydrochloric acid in a liter of water and it's still a strong acid, because when we talk about strength, we're talking about how well it dissociates. So a bucket of concentrated hydrochloric acid is just as strong as a drop of hydrochloric acid in a liter of water. Concentration has to do with that thing called molarity, how much is in that solution. So strong acid or base is strong no matter how dilute it is. Strong acids and bases are very soluble in water and good conductors, are good electrolytes, so they're good conductors of electricity. When we say they're very soluble, again, we're talking about the dissociation. Weak acids and bases are slightly soluble in water and are poor electrolytes. So there's your review. Hope you enjoyed it.